Okay, so this is a set of information about a big topic in mathematics and how calculus pertains to it called optimization. Okay, so in optimization, you're basically taking a quantity that's controlled by other independent variables and trying to figure out the state of those independent variables that will either maximize or minimize that quantity. Okay, we have a key tool here, and it's a thing called Fermat's theorem. Okay, not to be confused with Fermat's last theorem, but we're just going to call this Fermat's theorem. Fermat's last theorem is about something different. Fermat's theorem says that if f is differentiable on some open interval a b, and if x is an element of that interval, such that f of x is a local max or min. So everything nearby f of or nearby x is either let's try it this way. In its neighborhood, x is either going to make f maximized or it's going to make it minimized, okay? So if I have a local maximum or min, so all the numbers that are nearby that number are either higher or lower than that number, right? Then the following has to be true. Then we get that the derivative of f at x must be 0. Aha, so that's pretty important. Okay, so this makes sense, because if f has a local maximum, I'm going to get a horizontal tangent here, right? So this means that f prime of x is 0, or if f has a local minimum, I also get a horizontal tangent at that point. It doesn't mean it's absolute maximum because, it doesn't necessarily mean it happens at an absolute maximum, but it can happen at a local maximum, local minimum. Now, note, this is not true in backwards, okay? If I have the derivative being 0, that doesn't necessarily mean it's a local max or min. It's just telling me that if I have a local max or min and f is differentiable at that point, then the derivative has to be 0. So this gives me the ability to kind of narrow down the number of values that an absolute maximum or an absolute minimum can occur at. Okay, there are 3 places where I can find candidates for absolute max or absolute min. One is that if I have the endpoints of a domain, it is possible that the end point of the domain can be the place where the local maximum or the local minimum occur. Now, this is critical because the AP exam will do this. They will put one of the max or the mins at an endpoint of a domain, and people will miss this because they'll forget to check the endpoints. Really, really, really important. Always check the endpoints. Number 2, well, if the function has points of non-differentiability, so points of non-differentiability, we have to check those because they're not governed by Fermat, because Fermat assumes that you're differentiable at those points. So you could have a max or a min at a point of non-differentiability. Think of the absolute value function has an absolute minimum at the point of non-differentiability. So you have to check those too. Note also continuity here. So if it's not continuous, it's non-differentiable. Okay, so you have to check those as well. Okay, so discontinuity implies non-differentiability. All right, last one is by Fermat, points where f prime of x is 0. Okay, so this takes the infinite number of points that are in a function and narrows it down to a finite number, hopefully finite. The endpoints of the domain points of non-differentiability and points where the first derivative is 0. Now, we do get a little bit of help here. We can use the second derivative to speak about whether or not something is a local min or a local max. So this is what we're going to call the second derivative test. Okay, so the second derivative test tells me that if f prime of x is 0, then I look at the second derivative, okay? And if the second derivative at that point is negative, then I have a local max. Why is this? Because, well, I have to be this way. See, because this derivative is 0 and it's concave down gives me a local max. If the second derivative is positive, then I have a local min. Okay, because again, first derivative is 0, gives me the horizontal tangent, but I am concave up because the second derivative is positive, which means I have a local minimum. Everything else is higher than me in my neighborhood. Okay, so the second derivative test can give me some guidance as to where my absolute and absolute max and absolute min are, because I can rule out like the local mins are not going to be absolute maxes and the local maxes are not going to be absolute mins. So this can be used to guide some of my work here. Okay, so the best thing I think we can do here is to work a couple of examples. Let's say a manufacturer is producing an item and they've determined the following cost equation. That cost is equal to 8x squared minus 176x plus 1800, right? So like their fixed cost is 1800. No matter how many of these things they're manufacturing, it's going to cost them $1,800. Their variable cost is here, telling me, if I produce X units, I see some variation in my cost. So the question is like, when do I minimize the cost here, right? So the first thing I need to note is that there is an endpoint of the domain. My domain here is strictly 0, and in theory, I can make an infinite number of units, right? But I do have an endpoint at 0. This function is continuous everywhere. It's a polynomial, so it's going to be differentiable everywhere, so I don't have points of non-differentiation, but I do need to know where the derivative, which is going to be 16x minus 176. I set that equal to 0, gives me 16x is 176, gives me x is 11. All right, so at this point, I have two critical points. I have 0, the end of the domain, and 11, the only place where the derivative is equal to 0. So one of these has to be the location of the absolute minimum. All right, so what do? I just plug them in. C when x is 0 is going to be 1800, because that's clear from this. C when x is 11 gives me 8 times 11 squared minus 176 times 11 plus 1800 works out to be 832. Okay, so my minimum cost occurs by producing 11 items, and the total cost for those 11 items will be $832. So there we go. This is my minimization game here, right? So I have minimized the total cost of producing an item. So this is not the total cost of production, but the total cost per item drops to $832 when I have 11. If I produce less than 11 or more than 11, that cost is going to go up. Why do I know this? Because the only places where the cost can be minimized in this framework are at the endpoint of the domain, 0, or when the derivative is 0, 11, and it's the smaller of the two results. All right, so let's do one that involves a little bit of geometry here. All right, so looking at a little bit of geometry here, we're going to build a box. We're going to build an open box. We're going to start with a sheet of material that is 24 inches on one side and 18 on another. And the way we're going to build this open box is we're going to cut corners out of each side that are the same side, and then we're going to fold up the remaining pieces and make a box. Okay, so we'll call that X, right? So I want to maximize the volume of this box. So how big do I have to cut these corners to make this box as large as possible? Well, the height of the box, if you think about this thing, right, I'm going to get a box here in the end. Open box with four little squares sitting off here over to the side that I cut out. That's waste, right? So the height of the box is X. The width of the box this way is going to be 24 minus 2 of those X's. And this will be 18 minus 2 of the X's there. So my volume is X times 18 minus 2X times 24 minus 2X. Well, let's see, a little bit of mathing here. We get X, let's see, that's 432 minus 84X plus 4X squared, which means that I have 4X cubed minus 84X squared plus 432X is the volume of the box. Okay, so I do have a domain. Restriction, I'm restricted 0 on one end. I had to keep it as the flat sheet of paper. And at most I can go 9, right? Because 9 and 9 and that side's gone. So my endpoints of my domain are 0 and 9. Now, it's pretty clear that 0 and 9 are going to be like minimums, because 0, I have a box that has no volume, and 9, I am also going to have a box that has no volume. So those are going to be minimums. All right, so let's take dv dx to figure out where the derivative is 0. This is going to give me, what, 12x squared minus 100 and that's going to be 60, right? 168x, right? 168x, okay. Great. So what do we got to do? We got to set that thing. Oh yeah, oh no, sorry, and plus 432, right? So we got to set this thing 12x squared minus 168x plus 432 equal to 0. I believe this is divisible by 12, so I'm going to get x minus 14x plus 36 is 0. Okay, I don't believe that's factorable. So we use the quadratic equation, 14 plus or minus the square root of 196, right? B squared minus 4ac, which is going to give me 144 there, all over 2. I popped that thing through the calculator, and I end up with 3.4 or 10.6. But I can rule that one out because my domain is between 0 and 9. So I only get the 3.4 as the possibility. Logic dictates that that's going to be the maximum because these other two critical points are the minimum. It's clear that if x is 0, the volume is 0. If x is 9, the volume is 9. The volume when x is 3.4 is 3.4 times, let's see, 18 minus 2 times 3.4, I think is 17.2, or that's the 24. 24 minus 2 times 3.4 is 17.2. 18 minus 2 times 3.4 is 11.2, which gives me approximately 654.6 3.976 cubic units. So the maximum occurs when the snipping is done at 3.4 inches, which is going to give me this 654.976 cubic units of volume. Okay, so I was able to identify 3 critical points, the 2 endpoints of the domain, and 1 volume or variable value for the variable that's inside the domain. And of the 3 critical points, this one yields the highest possible value. So that's my absolute maximum. All right, so let's look at one more. Okay, so another type of problem is like an inscribed rectangle type problem that they like to do with. And they're going to say, okay, so let's say I have a semicircle and it has a radius of 4. Right, so the distance from here to here is 4 units. Okay, and now what I'm going to do is I'm going to inscribe a rectangle inside of this. And the question is now, like, what's the maximum area that this rectangle could possibly have? All right, so the trick to this thing is to visualize it in like the coordinate plane and put this thing, that's getting ugly. Let's make that a little neater. Whoop. I don't want that one going away. That one was neat. All right, so let's go this way, and we're going to put the center of this whole thing at the origin. Okay, and what we're going to do is we're going to call this point x, y. Now I have some constraints in my problem. This is 4, this is 4, this is negative 4 because the semicircle has a radius of 4, right? This is the point xy, which means that the distance from here to here, right, so that distance right there is x. Okay, which means that if that's x, let's see, I know something's going on here. I know that on that semicircle, x squared plus y squared has to equal 4. Or not, yeah, that's not true. Has to equal 4 squared, right? So x squared plus y squared has to equal 16, right? So ultimately, y squared is 16 minus x squared, which means y is equal to the square root of 16 minus x squared. And I can ignore the negative here because this y value on that part of the semicircle is always above the x-axis. So I can ignore the negative, right? So if y is this, right, and my square is, let's see, the area of that square is going to be 2x times y, or that rectangle is 2x's times y, which means it's 2x times the square root of 16 minus x squared. That's my area. Okay, so I have some domain restrictions. The smallest value that x can be is 0. The largest value x can be is 4, right? So, and at either of those, the area of the rectangle is 0. So those aren't the maximal area. So what is left is to figure out when is this thing's derivative equal to 0, right? So let's see. I think I can rewrite this a little bit, right? Let's be kind of clever about this here. I think I can write this as 2x times 16 minus x squared to the half. Means dA dx is going to be x times 16 minus x squared to the negative half, right? Oh, wait, that's not right. Let's be a little more cautious here, right? So this is first times the derivative of the second plus second, right, times the derivative of the first, which is 2. Okay. So let's see, that 2 and that half are going to cancel. So I think this gives me negative 2 x squared, yeah, negative 2x squared over 16 minus x squared plus 2 times the square root of 16 minus x squared, right? And this is a square root there. Okay, so gives me that, right? So let's hold that thought and let's set that thing equal to 0, right? So let's get a little extra room here. So where we left on the last screen was negative 2x squared over square root of 16 minus x squared plus 2 times the square root of 16 minus x squared is equal to 0. Well, let's bring that over there. Okay. That's negative, right? And, let's see, I think at this point, because we can't let x equal 4, right? Because then the whole thing goes to 0. I think at this point I can multiply both sides by the square root of this. It's going to give me 2x squared is equal to negative 2 times 16 minus x squared. Yeah, pretty straightforward there. The negative 2's, they go away, right? So that gives me x squared is 16 minus x squared. 2x squared is equal to 16. X squared is 8. X is square root of 8. And why don't I need the negative here? Because x, because of the way the problem sets up, x is necessarily positive. So let's see. I have 3 critical points then. I have 0, square root of 8, and 4, right? But I know 0 and 4 yield 0, so my maximum has to be when x is the square root of 8. So that's going to means that my maximal area is going to be 2 times the square root of 8 times the square root of 16. Let's see, minus the square root of 8 squared is 8, right? So this gives me 2 times the square root of 8 times the square root of 8, which is 6, that's just 16. So my maximum occurs when x is square root of 8, and the maximal area of that rectangle is 16 square units. All right, so you can go back, take a look at that drawing, see how that all plays out. So I'm giving a couple of ideas of how optimization works. You write one value in terms of another, and then you look at places where you either have an endpoint of a domain, a point of discontinuity, or a place where that function is its derivative is equal to 0. And you check those points, find out which one has the absolute maximum or absolute minimum that you need, and that's how you solve an optimization problem. All right, thanks.